Imagine an operator opening the safety guard of a robotic cell while the robot is still moving. The machine detects the open door and immediately stops the hazardous movement. But how do we know that this safety function is actually safe enough? What happens if the door sensor fails? What if the safety controller develops a fault? And how reliable does the complete safety system need to be? These are exactly the kinds of questions addressed by ISO 13849, one of the most important international standards for the functional safety of machinery. In this video, you will learn how ISO 13849 takes us from an identified machine hazard to a properly designed and verified safety-related control system. We will look at safety functions, required performance levels, the 5 system categories, and the key factors that determine the achieved performance level, including MTTFD, diagnostic coverage, and common cause failures. We will then bring everything together using a practical guard door safety function and see how verification, validation, and systema fit into the overall engineering process. By the end of this video, you should have a clear understanding of the complete ISO 13849 methodology and how its most important concepts work together. So let's start with the fundamental question. Why do modern machines need functional safety in the first place? The key challenge in machine safety is that the components responsible for protecting people can themselves fail. A safety sensor may no longer detect that a guard door has been opened. The signal from that sensor may never reach the safety controller. The controller itself may develop an internal fault. And even if the correct stop command is generated, the output device responsible for stopping the hazardous movement may fail to respond. In all of these situations, a safety function that appears perfectly adequate during normal operation could potentially fail exactly when it is needed. This is the fundamental problem addressed by functional safety. Functional safety is not simply about creating a control function that works under ideal conditions. It is about designing safety-related control functions so that failures and foreseeable faults do not lead to an unacceptable level of risk. Consider a robotic cell protected by an interlocked guard door. When the door is opened, the hazardous robot movement should stop before a person can reach the danger zone. But achieving this reaction once is not enough. Engineers must also consider what happens when individual components fail, and whether the overall safety architecture still provides sufficient protection. This is where safety-related control systems differ from normal machine control. A conventional control function may primarily be optimized for productivity, availability, or process performance. A safety-related control function has an additional objective. It must provide a defined level of risk reduction, and this required level is not identical for every application. A function protecting against a relatively minor hazard does not necessarily need the same safety performance as a function protecting against potentially fatal robotic movement. ISO 13849 therefore uses a scalable engineering approach in which the required safety performance depends on the risk associated with the individual safety function. To understand how engineers determine this required level of protection, we first need to see where ISO 13849 fits into the overall machinery safety process. So how do engineers determine how much safety performance is actually required? The answer begins before ISO 13849 is applied. Machinery safety normally starts with a systematic risk assessment. A central standard for this process is ISO 12100, which provides the general methodology for identifying hazards, estimating and evaluating risks, and selecting appropriate risk reduction measures. Imagine again our robotic cell. Engineers first identify the hazardous situations associated with the machine, such as access to the robot, while hazardous movement is still possible. They then evaluate the associated risk and determine how that risk should be reduced. Wherever risk reduction depends on the machine control system, a safety function can be defined. In our example, one safety function could be, when the guard door is opened, hazardous robot movement must be stopped. But defining the function itself still does not tell us how dependable it needs to be. This is where the required performance level, abbreviated as PLR, becomes important. The PLR represents the level of safety performance required from the safety-related parts of the control system for that particular safety function. Once this required level has been established, ISO 13849 provides the framework for designing and evaluating the corresponding safety-related control system. This may include the input device that detects the open guard, the safety controller that processes the information, and the output elements that bring the hazardous movement into a safe state. So ISO 12100 and ISO 13849 should not be viewed as competing standards. They address different parts of the same overall machinery, safety process. ISO 12100 helps us understand and reduce the machine risk, while ISO 13849 becomes particularly important when that risk reduction depends on safety-related control functions. And this brings us to the next important step. Before we can evaluate a safety-related control system, we need to understand more precisely what a safety function actually is and how the required performance level is associated with it. We have now seen that ISO 13849 becomes relevant when risk reduction depends on a safety-related control function. But before we can design the corresponding control system, the safety function itself must be clearly defined. To understand this, let's continue with our robotic cell. The robot can perform fast and powerful movements that may cause serious harm if a person enters the operating area at the wrong time. The hazardous movement itself represents a source of potential harm. A hazardous situation can arise when someone gains access to the protected area while this movement is still possible. One way to reduce this risk is to install a physical guard with an interlocked access door. But the guard door alone does not create the complete safety function. The control system must detect when the door is opened and react appropriately. We can therefore define our safety function in simple terms. Opening the guard door must stop the hazardous robot movement. This definition gives us a clear relationship between an initiating condition and the required safe reaction of the machine. In a real engineering project, of course, the specification would normally contain additional details. Engineers may need to define stopping behavior, response times, operating modes, reset conditions, interfaces, and other requirements relevant to the specific machine. But the fundamental idea remains the same. A safety function describes what the safety-related control system must do to achieve or maintain a safe condition. And each safety function is considered individually. A machine can therefore contain many different safety functions, and they do not necessarily require the same level of safety performance. For our guard door function, the preceding risk assessment determines the required performance level, or PLR. This gives us a target for the safety-related control system that we are about to design. But that raises another important question. What exactly does a performance level tell us? And what is the difference between PLA, PLB, PLC, PLD, and PLE? That is the next piece of the ISO 13849 methodology. This brings us to one of the central concepts of ISO 13849, the performance level. ISO 13849 defines 5 performance levels, ranging from PLA to PLE. These levels represent different capabilities of a safety-related control system to perform a safety function under foreseeable conditions. As we move from PLA toward PLE, the required safety performance increases. PLA represents the lowest level within this classification, while PLE represents the highest. This does not mean that every safety function should automatically be designed for PLE. Instead, the required level should be appropriate for the risk associated with the individual safety function. This brings us back to the distinction introduced on the previous slides. The required performance level, or PLR, represents the target derived from the risk assessment. The achieved performance level, on the other hand, describes the safety performance that the implemented safety-related control system can actually provide. These are two different things. Simply specifying PLD, for example, does not mean that the implemented system automatically achieves PLD. Engineers must design the safety-related parts of the control system and then evaluate whether that design actually reaches the required level. At the end of this process, the achieved performance level is compared with the required performance level. In simple terms, the achieved PL must be at least as high as the required PLR. For our guard door safety function, we could therefore imagine that the risk assessment defines a particular PLR. The engineering task is then to design the sensor, logic, and output subsystem so that the complete safety function achieves that target. But this raises the next question. What makes one safety-related control system capable of achieving a higher performance level than another? One of the first pieces of that answer is the system architecture, and in ISO 13849, this brings us to the different categories. ISO 13849 describes the architecture of safety-related control systems through 5 categories: B, 1, 2, 3, and 4. These categories describe different approaches to dealing with faults within the safety-related parts of the control system. Categories B and 1 are based on comparatively simple architectures. Category 1 builds on the basic principles by placing greater emphasis on the reliability and proven characteristics of the components used. Category 2 introduces testing. The safety function is checked at suitable intervals so that certain faults can be detected rather than remaining unnoticed indefinitely. Categories 3 and 4 move toward redundant architectures. Instead of relying entirely on one functional channel, multiple channels can contribute to maintaining the safety function when individual faults occur. Diagnostic measures also become increasingly important. Category 3 requires that a single fault does not lead to the loss of the safety function, although not every fault necessarily has to be detected. Category 4 goes further by combining high fault tolerance with extensive fault detection, including consideration of fault accumulation. One point is particularly important. A category is not the same thing as a performance level. We cannot simply say that Category 3 equals PLD, or that Category 4 automatically equals PLE. Architecture is only one part of the evaluation. The actual performance level also depends on how reliable the components are, how effectively dangerous faults are detected, and whether common causes could defeat redundant parts of the system. These factors must therefore be considered together with the category before we can determine the achieved performance level. The first of these factors is the category, which describes important architectural characteristics of the safety-related control system. The second is MTTFD, meaning mean time to dangerous failure. In simplified terms, MTTFD represents the reliability of the components with respect to dangerous failures. A system built from components that are more likely to fail dangerously cannot be evaluated in the same way as an architecture using highly reliable components. The third factor is diagnostic coverage, abbreviated as DC. Diagnostic coverage describes how effectively the system detects dangerous failures. This is particularly important in architectures that use monitoring or redundancy, because a fault that remains undetected may influence the safety capability of the system over time. The fourth factor is common cause failure, abbreviated as CCF. Redundancy is valuable only if the redundant channels have sufficient independence. For example, two separate channels may appear fault-tolerant, but a shared power supply problem, environmental influence, or design weakness could potentially affect both channels at the same time. Common cause failure measures are therefore used to reduce the possibility that a single underlying cause defeats multiple parts of the safety architecture. ISO 13849 brings these aspects together when evaluating the achieved performance level. The architecture matters. Component reliability matters. Diagnostic effectiveness matters. And the independence of redundant elements matters. The detailed evaluation involves additional requirements and relationships, but the key idea is straightforward. No single parameter determines the safety performance of the system by itself. All relevant characteristics of the safety-related control system have to work together to achieve the required PLR. We can now apply this logic to the guard door safety function and see how the individual elements form one complete safety-related control system. In our guard door example, the safety-related control system can be divided into three basic parts: input, logic, and output. The input subsystem detects the condition that should trigger the safety function. Here, an interlock monitors the position of the guard door and provides the relevant safety information when the door is opened. This information is passed to the logic subsystem, typically represented by a safety controller or safety PLC. The controller processes the input according to the defined safety logic and generates the required command for the output subsystem. The output subsystem then acts on the machine. Depending on the application, this could involve contactors, a safety-capable drive, or other components responsible for removing or controlling the hazardous movement. Together, these elements implement our safety function. Opening the guard door causes the hazardous robot movement to stop. An important point is that we evaluate the complete safety-related control chain. Using a highly reliable safety sensor alone does not guarantee that the overall function achieves the required performance level. The logic and output elements must also be considered, together with the architecture and the relevant failure behavior of the complete implementation. This is why engineers cannot simply select individual components marked for a certain safety application and assume that the complete machine automatically achieves the same performance level. The implemented safety function must be evaluated as a system. For our robotic cell, the result of this evaluation is the achieved PL. We can then compare that result with the PLR established earlier during the risk assessment. But demonstrating the required performance level is only one part of completing the safety function. We also need to confirm that the function has been implemented correctly and that it actually provides the intended protection in the real machine. Once the safety-related control system has been designed and its achieved performance level has been determined, the result must be checked against the original requirements. This is where verification and validation become important. Verification asks whether the implemented design satisfies the specified requirements. One important part of this is comparing the achieved PL with the required PLR. If the achieved performance level is lower than the required level, the design does not provide the required safety performance and must be reconsidered. But achieving the required performance level alone is not sufficient. We also need validation. Validation considers whether the safety function has been correctly implemented and actually provides the intended protection within the real machine and its intended application. For our robotic cell, this means more than evaluating reliability data on paper. Engineers must confirm that opening the guard door really produces the required safe reaction, that the complete function behaves correctly under the relevant operating conditions, and that the specified safety requirements have been fulfilled. In practice, engineers can use specialized tools to support parts of this process. One widely used example is Systema. Systema stands for Safety Integrity Software Tool for the evaluation of machine applications. The software supports engineers in structuring safety-related control systems and evaluating parameters relevant to the achieved performance level. But the role of the tool is important to understand. Systema does not make the engineering decisions. It does not determine whether the original risk assessment was correct, and it cannot compensate for incorrect assumptions or unreliable input data. The quality of the result still depends on the quality of the engineering behind it. With verification and validation completed, we can now connect all of the individual steps and look at the complete ISO 13849 engineering workflow from the original machine, risk to the final validated safety function. With verification and validation completed, the individual elements now form one continuous machinery, safety engineering process. It begins with the machine and its hazards. Risk assessment establishes where additional risk reduction is necessary and where safety-related control functions are required. Those safety functions are then specified together with their required performance levels. The corresponding safety-related parts of the control system are designed using suitable input, logic, and output elements. Their architecture, component reliability, diagnostic capability, and resistance to common cause failures are evaluated to determine the achieved performance level. Verification then confirms that the implemented design satisfies the specified requirements, while validation provides evidence that the complete safety function behaves correctly in the actual application. And the process does not simply end once the machine starts operating. The safety-related design, assumptions, calculations, test results, and other relevant evidence need to be documented and maintained throughout the machine lifecycle. Modifications can also affect existing safety functions and may require parts of the assessment to be revisited. This complete chain is what makes ISO 13849 much more than a calculation of a performance level. It provides a structured engineering approach for connecting machine risk with dependable safety-related control functions. In this video, we have focused on the overall methodology and the relationship between its most important concepts. If you want to go beyond this introduction to ISO 13849, we offer comprehensive online training programs covering machinery safety and functional safety. The complete ISO 13849 course goes deeper into performance levels, categories, MTTFD, diagnostic coverage, common cause failures, verification, validation, and the practical application of Systema. You can also find our ISO 12100 course, which covers the broader machinery safety process, including risk assessment and systematic risk reduction. You can find the links to the courses in the video description and in the pinned comment below. If you found this video helpful, please consider giving it a like and subscribing to the channel. We regularly publish educational content covering machinery safety, functional safety, automotive engineering, aerospace systems, and other engineering standards. Thank you very much for watching, and I look forward to seeing you in the next video.